Hello, welcome to Light as a Particle. We've done light as a wave, now we're going to do light as a particle, and we're going to start off with what's called black body radiation. Now, first of all, we need to have a bit of history. So, Max Planck was a very important physicist and pretty much started what we would call modern physics with his discoveries. And that's what he looked like when he was at the end of his career or midway through. But what did he look like when he was younger? Like that, on a bad hair day. So he was born in 1858, got a PhD by 1879. You can do the maths. He deduced the relationship between energy and the frequency of radiation. And, with a capital and, that radiation could only be as discrete values or quanta. And this was quantum theory, and it was the beginning of modern physics. Before that, it was all governed by traditional classic wave theory and Newtonian physics, but quantum theory was basically what we now call quantum mechanics. It was the start of where things started to go a bit weird, and the physics was harder and harder to actually conceptualize, but it was true because people could make these observations and do the physics. And a very simple equation that he based his work on, which was E equals hf, and we'll look at that in more detail, but the E is the energy of a photon, and F is the frequency of the photon, and H is a constant, and we now call H Planck's constant in recognition of his work. And his work was a turning point in physics, as I said, and he got the Nobel Prize in 1918. He did, however, have a fairly troubled and tragic life, in that during the period when the Nazis were in government, because he was a German or an Austrian, I think, can't quite really remember, he was openly opposed to the Nazi policies, and you can imagine what that was like in Nazi Germany. And so it was a difficult time for him. There's been a lot of biographies about him, and they're all very interesting because it was a very interesting time to be a scientist, and not only a scientist, a physicist, but not only a physicist, but a physicist in Nazi Germany. One of his sons was executed for his role in the attempt to assassinate Hitler in 1944, which was the one where they put the bomb under the big desk, and the leg of the desk saved Hitler. It was when people were starting to recognise that the war was doomed for Germany, but pretty tragic circumstances. And then he died in 1947, not long after the end of the Second World War. So, what's black body radiation? Well, all objects radiate energy unless they have a temperature of absolute zero. And absolute zero is minus 273 degrees Celsius, and that's when everything stops. So everything radiates energy. The maximum energy which can be radiated from an object is called the black body radiation. So that's the maximum energy you can get. And a black body is a theoretical object that is a perfect absorber and emitter of radiation. So it's modelled as perfection. It's not what actually happens in real life, but there are some objects that get very close to being theoretically perfect, whereas everyday objects, lots more things are happening where energy is lost or transformed into other forms. Now, the radiation given off by a black body occurs in a wide range of or spectrum of wavelengths, and based on careful observations and quantum theory, Max Planck produced an equation to model the observed radiation curve, and his discovery is considered one of the most important in the field of quantum physics. And this was his equation. We don't need to know that. It's just there for interest's sake. And that seems a bit abstract, but we're going to work our way through it, and hopefully you'll get the idea of what we mean by that. And you might come back and have a read of that again once we've done some examples. So here we have a graph which is intensity, so that's basically the amount of photons of wavelengths. This is the wavelengths, recognizing that light can be made up of all these wavelengths, and these are the curves for different temperatures from a object. And so this is a cooler object, then a hotter object, and then a hotter object as well. And this is the classical theory. So before Max Planck, this is what people thought would happen. Now recognize that this is low energy wavelengths and this is high energy wavelengths. So the shorter the wavelength, the more energy we have in the photons. And so what they would say, that as it heats up, you get an exponential growth of these shorter wavelengths. And what Max Planck actually observed was this, that as the temperature increases, the peak of the black body radiation curve moves to higher intensities and shorter wavelengths. So there's the peak there, it moves from there, so shorter wavelengths and higher intensity, and then it moves to there as well. And that's what he observed, and it didn't fit the classical theory at the time. Note, as temperature increases, the total energy output per second increases. As temperature increases, the peak wavelength became less. By 1000 degrees Kelvin, some of the radiation has reached the red end of the visible spectrum. Okay, so the object is glowing red hot. You can actually see it glowing because it's giving off wavelengths of light that are in the visible spectrum for red. When the peak is within the visible spectrum, the object is glowing white hot, and we'll see some examples of that shortly. For a radiator, so something like a bar heater, it's not a perfect black body, and the lines of the graph would be a similar shape, but the peaks would be lower because energy is being transformed into other things. So there's a couple of things I'm going to show you now. Let's see if I can bring them up. We've got to go here. Now, what one? Here we go first. We'll do this one. So here we have the blue line is your classical interpretation of what happens to an object as you heat it up and the radiation given off, and the green one is Planck's interpretation. And as we increase, and frequency is increasing, so these are high energy, these are low energy, and as we increase the temperature, okay, you start getting this curve which was observed. Okay, before that people hadn't actually observed them, and the peak is moving as the temperature increases. The peak moved from there to there, but also increased in intensity. What's this one? Okay, so this is another one. This is what the object would look like, and if we started a cool object, you can see that the peak is actually off here, so it's actually not radiating much in the visible spectrum. This is the amount of light in the visible spectrum, and so it would just appear yellow at this temperature because we're getting all these reds and yellows being irradiated. As we warm it up, though, notice that now the pink is in the pretty much the middle of the visible spectrum, and so it now appears white hot. So think of something like your bar heater or the elements in the stove, if you've got an electrical stove, how they change temperature as you heat them up. And so this is white hot, and if we heat it up some more, it starts to actually get a blue color because the peak is now in the violet and the ultraviolet, and then it starts getting a lighter blue color. So we're up to 10,000 Kelvin, 12,000 Kelvin, and notice that here we've peaks way out here, so this is giving off ultraviolet light, but we're still getting blue, so the color hasn't changed much, but it's significantly hotter. Now what's this one? Oh yeah, this is, people look at stars, and similarly this is what the star would look like, and they can tell the temperature of the star by the colour of it. And so a cool star is yellow, and a hotter star gets yellowy, and then white. And this is the black body radiation curve, and as you move into it, it goes into blue, and then like so. And this one's similar. Here we've got the temperature, this is our wavelength, this is our intensity, and this is what we're showing for the Earth at about 345 degrees Kelvin. If we heat it up, so we move it, whoops, I went too far. If we move it up to the temperature of an oven, now we need to zoom out, zoom in, sorry, and we need to make that smaller. I've got this all around the wrong way. There we go. So we're zooming in. Notice, so we went from Earth to an oven, okay, and as we increase it to a light bulb, okay, and let's zoom in. So here's the peak. We've just zoomed in, so we're changing the scale. It gets a bit tricky. This one will be on your OneNote, so you'll be able to play with it. If we get it to a light bulb, you can see now that there's light being given off, and if we make it a better light globe, keeps wanting to zoom in, we can get different colours, and this is what's happening here. But enough of that. You don't want to watch me playing with it, you can do that yourself. So let's just get back into this. So that's all that, and we've done that. Good. So this is where black body radiation fits into modern physics. There's a whole lot of things here that are way out of our course and we don't need to know, but it was a very benchmark discovery that led to all these other things and increased our understanding. And in terms of the applications of the formulas, there's all these variations on it, which again increased our knowledge and understanding. Way out of our course, don't worry, it just shows you that there's a lot of maths in physics. If you go on to uni and do physics, you'll do a lot of maths. Now, some other examples. Now, I mentioned that people look at stars and look at the black body radiation. These are just some examples. This is a very cool cloud of gas. It's only at 600 degrees Kelvin, and this is what the curve looks like, and you can hardly see it. It's just there, and you have to actually use a radio telescope to see it. If we go to a young star, which is at about 600 degrees Kelvin, we see that the curve has entered the visible light, and that's it there. And so we can tell a lot about the star in terms of the radiation that it's giving off. And our sun, sitting here, this is the curve here because it's at about 6,000 degrees Kelvin, so it looks yellowy, whitish yellow to us. And then there's some very hot stars, 6,000 degrees Kelvin. Their peaks way out here in the ultraviolet, so we still get a visible spectrum, but if we were to look at them, we'd actually need to look at the ultraviolets to tell more about them. Here's someone holding a hand. Well, it's a bag, we can't actually see what's here, but if we used an infrared camera, we could actually see that the radiation was being given off by a hot body, and that's what we're using, and we can tell the temperature from the radiation being given off. Something like I mentioned hot plates, but you could also, this lava is obviously very hot, but we can tell its temperature by the colour of it, and we can tell that it measures at about 1000 to 1200 degrees Celsius by the colour of the radiation given off. And there's some examples of black body radiation and how we use it. What happened there? Whoops, I clicked on that. That wasn't good. Let's go back. Now, this is the Earth's radiation. So the Earth isn't a perfect black body, but we can look at the radiation and tell the temperature and how much energy is being given off it. What about our universe though? That's pretty interesting. Well, the universe is considered a perfect cavity, has no leaks, and therefore it contains all its radiation, and therefore it is a perfect black body. and it must have a certain temperature, and people have calculated, and the temperature of the universe, if we sampled everywhere, is only 2.728 degrees Kelvin, so very close to absolute. So it's a very cold place. So places like Tasmania we might think is cold, but it's actually a hot spot in the whole universe. Now the curve for this temperature is in the microwave region, and so we've been able to, how do we know this and how does it fit in? Well, the universe is now thought to be between 12 and 15 billion years ago. When it rapidly expanded, some of the radiation that was in the smaller universe condensed to matter, and the universe continued to expand and expand. Now, because not all the radiation condensed to matter, the leftover radiation was stretched out as the universe expanded, and that cooled it because the particles and everything became further and further apart. And that's what we're measuring in the universal black body temperature for the universe. So small variations in this black body radiation can be looked at, and we can see that there's lumpiness in our universe, and in the early universe it was lumpy, it wasn't all smooth. Now that's a bit of a quandary to people who study the Big Bang Theory and how the evolution of the universe, and they're working on ways of solving it. But now we know that this lumpiness was within the first femtosecond or so, which is a very small fraction of a second. And we now also know that we can much more accurately date the universe as 13.7 billion years old, using the inflation model and various other mechanisms. So what did the Earth look like at 1 times by 10 to the minus 15 seconds old? So that's a fraction of a second. It looked like this, and this is a photograph of the background microwave signature of the universe going back in time, and you can see it's not uniform, it's lumpy, and it's an expression of the distribution of matter within the universe at that time. Pretty amazing image, and that's been photographed from WOMAP, and this is looking through the entire sky. So it's a bit hard to represent a sphere that you're looking at, but this is a mapping representation of it. And this is how it's evolved, and it's called the cosmic microwave background radiation. It was discovered in 1965, and some people have already done that in their essay, and this is what they found. They just found a constant microwave hiss in the background. It was the earliest sound or representation of the universe. Then they sent out COBE to map it, and this was the image that they got. And now most recently WOMAP came up with a much more detailed image. Now this red line is just the disk of our galaxy, the Milky Way, and so people extract that and you get the other image. So from that to that, and you can see this distribution. This is what formed galaxies and various other things. Distribution of matter was not even at this time, 1 times by 10 to the minus 15 seconds into its existence. And from here the universe expanded, and so this was the inflation period, which happened in that milliseconds, and then the universe continued to expand to what it is now. So in the next video we're actually going to look in a bit more detail into photons. See ya.